Welcome back to the next section of Chapter 3. In this section, we're going to learn another process, and this one's called implicit differentiation. And this will allow us to find the derivative of a lot more types of functions. And remarkably enough, this is the last type of derivative, really, that we're going to be looking at how to find. All the rest that we're going to be doing with derivatives is going to be application. After this, you should be able to find pretty much any kind of derivative that we're going to be working with this year, with the exception of some hyperbolic trig if we get into that. And so, implicit differentiation is a process, and it's something that we can use with implicit equations as opposed to the explicit equations or explicit functions that we've been dealing with so far in pretty much your entire mathematical lives. An explicit function or equation is one that can be written as y equals something. It is possible that you can have an equation where you cannot get y by itself, so you cannot write it as y equals something. We can still find the derivative of that, though, using this process. So, an example of a type of implicit function would be y squared plus xy plus x squared equals 0. We cannot get y by itself here. And so, in order to do implicit differentiation, we are going to take the derivative of everything with each variable. So to find the derivatives here, we're going to start out y squared. The derivative of y squared is going to be 2y times the derivative of y. It's the chain rule. The derivative of y is just dy plus xy. Xy is going to be a product rule issue. So we could have u equals x, v equals y. So du equals dx, dv equals dy. And we can product rule this. So we have y dx plus x dy. And then the x squared plus 2x times the derivative of x. You might think, oh, the derivative of x is 1. Technically, kind of, yeah, we're going to call it dx. That's what the derivative of x is. Then equals 0, because the derivative of 0 is 0. So now we've taken the derivative of everything with respect to all the variables. Every one of these terms will have either a dy or a dx, because if it didn't, that meant it was a constant and it would be 0. So we're going to move all the dy's to one side, all the dx's to the other side. The dy's, well, everything's already on this side, so we're going to leave the dy's. We have that dy and we have that dy that are going to stay. So we'll have 2y dy plus x dy equals, and then we have some dx's that are going to move. We have y dx is going to move, and a 2x dx is going to move. So we subtract minus 2x dx and minus y dx. Everything on one side has a dy, everything on the other side has a dx. We're going to factor out the dy's and dx's. So we'll have a dy times what's left, 2y plus x equals, factor out dx, what's left, negative 2x minus y. And now we're going to divide, because what we want is we want dy over dx because that's the derivative. Yes, it's the other method of writing the derivative. We haven't used it too much yet this year, but the implicit differentiation is one of those places where it is so much more handy. So to divide this, it's actually a lot easier than you would think. We divide the dx over there, and we divide whatever is here over there. So we're going to have dy over dx equals negative 2x minus y over 2y plus x. That's it. That is the derivative implicitly. It doesn't look pretty. It doesn't have to look pretty. But that would be the slope to this equation wherever we might see the equation. To plug in a point, by the way, we would actually need an xy coordinate on the original equation. We can't just pick a point and plug it in. It should be something on the line itself. And we need both x and y in this case. We could be doing this with just an explicit function. In fact, we really do. But with explicit functions, if you did it this way, you would always have dy equals, because it's y equals or f of x equals. And so you'd have dy equals a whole bunch of stuff with x's. So everything would have a dx. The dx is already on that side. Factor out divide. You have dy over dx or y prime equals the derivative. So when it's explicit, we could do these steps, but we don't actually need to because it happens for us. However, there are some explicit equations that we can't really find the derivative of with what we know, but we can use implicit. So one of the types of functions that we can use implicit differentiation for that we can't really do without, at least not easily, we could put it into the definition, but it is rather tough, is find the derivative of y equals natural log of x. You might think, well, wait, no, we just did that. The derivative of natural log of x is just 1 over x. That's easy. Yeah, why is it 1 over x? Because I told you it was. That's not a good reason. You need to be more curious than that. Why is it 1 over x? Like I said that, it's like that doesn't even make sense. Why would it be 1 over x? We're going to find it using implicit differentiation. So, starting out, we have y equals natural log of x. We can take both sides of the equation to a power of e. So we can go e to the y, e to the natural log x, the same way we would have been solving for this in years past. We could have also written it using an exponent instead of a log. It's the same idea. But when we do this, e to the y is e to the y equals e to the natural log x is just x. Now we can take the derivative. We can find the derivative of e to the y. We were able to show what the derivative of e to the y was, at least mostly. So to take the derivative, we're going to have e to the something is going to be e to the something times the derivative of the something. Then equals the derivative of x is just dx. We can divide, so because we want dy over dx. So if we move the dx down, that's like leaving it with 1. Then divide by e to the y. So we have 1 over e to the y. We don't particularly want e to the y in the equation. What does e to the y equal? E to the y equals x. So we can plug that in. dy over dx equals 1 over x. That's why the derivative of natural log is 1 over x. You can find the same, or you can use the same process to show that the derivative of log of any base is what it is. And we can also use this when dealing with inverse trig functions. That's not inverse as in reciprocal like cosecant. That's inverse as in sine of -1. What's the derivative of sine of -1 of x? That's a very good question. We don't have anything to tell us that, but we do. We can take the sine of both sides, which would give us sine of y equals, the sine of the inverse sine goes away, so that just equals x. Take the derivative of both sides now. Sine is going to be cosine of y times dy equals dx. Divide to get dy over dx equals 1 over cosine of y. And so now we need to get rid of that cosine of y. We don't have cosine of y up here. We have sine of y, but we can use that sine of y because if you remember trig, that deals with right triangles. Y is going to be an angle, and then the sine is the opposite over the hypotenuse. That would be x over 1. We can plug this into the Pythagorean theorem. X squared plus this open spot will go question mark squared equals 1 squared. Subtract the x squared over. So question mark squared equals 1 minus x squared. Square root, that blank space will be the square root of 1 minus x squared. And notice we don't need plus or minus because it's a length. It will be positive. So this is square root of 1 minus x squared. Now we can deal with cosine. The cosine of y will be the adjacent divided by the hypotenuse. It's the square root of 1 minus x squared over 1, which is just the square root of 1 minus x squared. Plug that back in. dy over dx equals 1 over the square root of 1 minus x squared. And when I had to learn this, they just said you had to memorize it. That's what it was. Just memorize. I hate just memorize. I love being able to find it because I don't have to memorize this because this is a pain to memorize, especially when you get the rest of them that are all very similar, but just a little bit different. Being able to find it, it's just a couple steps, especially once you know what you're doing. It's a couple steps that go really, really quickly, and you can find these. The rest of them, by the way, are up here. Here, let me get rid of some of my work there so that we can see it. But these are the rest of them. In your assignment, you will be verifying those. They follow the exact same steps. But being able to do that, again, it saves time and space in your head because these are all very similar. A couple things to notice though, the regulars and the cos are very similar, except the cos are negative, just like the derivatives of the regular trig functions. And yeah, that would be that. There's another type of function that we can find using implicit differentiation, and that would be the function that's written as something like x to the x, where it's not a power function because it's not x to a power, that's just a constant. It's not an exponential function because it's not a constant to a variable. It's a little bit of both. So we can do that using implicit, however. If we want the derivative of y equals x to the 5x, we can do this by first taking the log of both sides. And when I say take the log, I mean take the natural log, because finding the derivative of a natural log is much, much easier than finding the derivative of a regular log. So natural log of both sides, we have natural log y equals natural log of x to the 5x. And we do that so that we can move this guy out in front. Natural log y equals 5x natural log x. Now we can take the derivative. Both sides, the derivative of natural log of y is 1 over y dy equals the natural log of 5x ln x. It's going to be a product rule again. So let's say u equals 5x, v equals ln x, du equals 5 dx, dv equals 1 over x dx. Notice all the derivatives will have to have dx or something in them, dx or dy. We can multiply 5 dx times ln x. I'm going to say 5 ln x times dx plus 5x times 1 over x dx. 5x times 1 over x dx. And this one, notice, by the way, x times 1 over x cancels. That's just 1. So this is really just 5 dx. Factor out the dx. 1 over y dy equals, we have our dx, 5 ln x plus 5. Get back to my red pen. We can divide, so dy over dx equals, and then we'll multiply the y up. So we have y times 5 ln x plus 5. We can plug in y because from the very beginning, y equals x to the 5x. So that means dy over dx equals x to the 5x times 5 ln x plus 5. So it shouldn't surprise us too much that the original function was back in this function, being that when we have a number to the x, that happens. You can actually find a formula for this where you don't have to do implicit every time, but based on what you have and the chain rule for both parts, it gets kind of messy. I know personally, I just do implicit every time, but I'm comfortable doing implicit differentiation. I'm comfortable working with logs. I'm comfortable working with the product rule. If you can get that level of comfort and be able to do this without too much thought, you don't have to memorize the weird formula that you might get by doing that. And so that's why we do this stuff. Anyway, with that, after you can find the derivative of pretty much anything that we're going to be looking at this year. After what we have the power rule, which gets x to a power. We have exponentials, logs, and then chain rule, product rule, quotient rule, and implicit differentiation. Oh, and the trig, that's pretty much everything we got. So, um, be working on these, be answering questions, be working problems, be asking questions, and as always, happy mathing.